Industrial applications require steel components to be increasingly lighter, stronger, and reliable. They need steel to be strong, but most of all, they need steel that can resist fatigue, because fatigue is responsible for the majority of all service failures. Fatigue happens when a metal component fails when subjected to a number of repeated loadings, even when the maximum load is well below its nominal strength. Years of research have shown that defects in steel, such as non-metallic inclusions, play an important role in initiating fatigue failures. These inclusions are larger in conventional steels and smaller in clean steels. They act as stress raisers that multiply the nominal load on the component to above its safe fatigue limit. This causes the formation of cracks that propagate under stress reversals, eventually resulting in failure. The importance of clean steel is clear when we look at a typical powertrain component such as a gear wheel. As the gear meshes, each tool is subjected to bending fatigue stresses at its root. Conventional steels contain a wide distribution of large inclusions. There is a significant possibility that a potentially damaging inclusion will coincide with the area of high bending stress. The result is premature failure. In a clean steel, the size and distribution of inclusions is closely controlled. This reduces the risk of fatigue failure. It is vital to quantify the cleanliness of a steel to verify that the required fatigue performance is achieved in the final component. For macroscopic inclusions, relatively crude visual methods are used to define the acceptable number of very rarely occurring large-sized inclusions. But these methods will not provide the information needed to define the performance of clean steels. Instead, we use ultrasonic testing at high frequency with samples immersed underwater. The immersed ultrasonic test shown here shows the major difference between conventional steel and a clean steel. To identify smaller defects, we also use automated scanning electron microscopy. In addition, we conduct actual fatigue tests on specimens. We combine all these methods to determine the size distribution and number of inclusions. The fatigue strength, reliability, and repeatability of clean steels can enable the design of components that would not be feasible using conventional steels. They also help to reduce size and weight for smaller, compact designs that use less steel. In many cases, selecting clean steel will add value as well as offering a cost-effective design solution. Ovako has taken clean steel to the next level with the IQ steel range of isotropic clean steels. Conventional steels with high hardness have a particular weakness when stressed transversely to the rolling direction. In some cases, elongated sulfide inclusions will reduce strength by some 300 megapascal. In contrast, the small, isolated, and evenly sized inclusions in IQ steel provide the isotropic properties that can withstand heavy loads in all directions. This makes IQ steel suitable for complex load cases, especially in powertrains.